Our next section is about nuclear transmutation. So chapter 21, section 3 is nuclear transmutations. These nuclear transmutations can occur when a nucleus is struck by either a neutron or a high-speed nucleus. Now, the neutron doesn't necessarily have to be going very fast because it's neutral, but the nucleus, if it's struck by another nucleus, because nuclei are positive, then they have to be going pretty fast to overcome that repulsive force. So they have to be going pretty darn fast. So when we're looking at nuclear transmutations, again, usually there's some particle, they strip it of their electrons, and then they get it up to a really, really high speed. In this case, they would do this with helium, and they would bombard it into a target of nitrogen-14. And then the product of that, we would get some hydrogen, would be an ejected particle, and then we would get a product particle that would be oxygen-17. And that oxygen-17 could be used for other things. So we'll find that nuclear transmutations, we can represent them using a shorthand designation. And the shorthand designation uses whatever our target nucleus is, whatever it is we're trying to start with. Our bombarding particle is right here. The comma is pretty much where the arrow would be. So the comma separates the reactants from the products. Here our ejected particle is a proton, so that's the hydrogen nucleus. And then our product nucleus is whatever is over here. So I want you to be able to, if I give you an equation like this, perhaps come up with the shorthand notation. And if I give you the shorthand notation, I want you to be able to come up with the full equation. So we're going to look at numbers 28 and 29. So here is number 28. So complete and balance the following nuclear reactions. Some of these are going to be nuclear transmutations and some are not. And if you're not sure what type it is, don't worry. I will tell you what type it is. Some of these we're going to talk about later, like fission. This reaction, by the way, is a fission reaction. So here we've got uranium-235. We hit it with a nucleus, and we end up with xenon-135, 2 neutrons, and we're going to get some other particle. And to get what that other particle is, we just need to do the math. So 235 plus 1 is 236. And then we're going to subtract away 135 from 236, and that's going to give us 101. And then we'll subtract 2 more because there are 2 neutrons there, and that is going to give us 99. So again, 235 plus 1 is equal to 135 plus 2 plus 99. 92 plus 0 is equal to 54 plus 0 plus 38. And so element 38 will go over here to our periodic table. Element 38 is strontium, so we'll put Sr. And in case you're wondering, this is called fission. And we'll talk about fission in a later section in this book. All right, here we've got californium-252. We hit it with a boron nucleus, and we end up with 3 neutrons and something else. So we'll do 252 plus 10. That gives us 262. And then we'll subtract 3 from 262, and that gives us 259. And if you don't believe me, get your calculator. 98 plus 5 is equal to 0 plus 103. And 103, I'll pull up my periodic table here. 103 is right there, and that is lawrencium, Lr. So that is lawrencium, Lr. All right, this is a nuclear transmutation. All right, you don't have to write these down, but I thought it would be useful. So nuclear transmutation. Yeah, anyway, that's supposed to say transmutation. There you go. Okay, So next, here we've got so hydrogen 2 plus hydrogen 3 gives us a neutron plus something else. So we'll do 2 plus 3 is equal to 1 plus 4. And 1 plus 1, that's 2, is equal to 0 plus 2. Well, 4, 2, we know that is helium. Well, this turns out to be a process called fusion, and we will talk about fusion again in a chapter. It's after the fission chapter. All right, 2 plus 3. So again, we've got hydrogen plus helium gives us helium plus something else. So 2 plus 3 is equal to 4 plus 1. And then 1 plus 2 is equal to 2 plus 1. Well, 1, 1, that's just hydrogen. That's hydrogen with no neutron in it. And so what's great about this particular process is that none of the reactants and none of the products are radioactive. And by the way, this is another fusion reaction. So neither of the reactants and neither of the products are radioactive, and it gives off an enormous amount of energy when you do this particular reaction. The problem is there's not a convenient way to do that reaction. The upside is it happens in the sun all the time, but that we don't live there. Okay, so next we've got helium plus aluminum gives us a neutron plus something else. So 4 plus 27, that's 31. That's equal to 1 plus 30. And then 2 plus 13 is equal to 0 plus 15. And element 15 is right here. That's phosphorus. All right, well, this is also a nuclear transmutation. All right, I managed to spell the word without fumbling all over it. All right, you remember when we were talking about stability patterns, and if there's an odd number of protons and an odd number of neutrons, then that usually indicates that it is radioactive. There are a limited number that are stable, but most of those are radioactive. Well, phosphorus is an example of that. Phosphorus 30. There are 15 protons and 15 neutrons in it. And it turns out that is not a stable nucleus. So let's look at the next one. 0 plus 30 is 30. And 1 plus 14 is 15. And that happens to be phosphorus. Well, this 0, 1, that is a positron. So this is positron emission. So that is positron emission. Okay, so now we've got 248, let's see, plutonium 248 plus calcium 48 gives us 3 neutrons plus something. This thing is going to be big, this thing over here. So let's do this. 248 plus 48. Oh my gosh, do I need to break out a calculator? I'm going to break out a calculator just because I haven't been sleeping enough. So, all right, I'm going to clear that. 244 plus 48 gives us 292. And then we're going to subtract 3, so minus 3. And that gives us 289. So we get 289. And then 94 plus 20. All right, I could do that in my head. That's 114 is equal to 0 plus 114. And 114, move that out of the way. 114 is flavorium. So 114 FL. All right, and that is another nuclear transmutation. Nuclear transmutation. All right, so for number 29 here, on this one, we're simply taking these shorthand designations and writing them as regular equations. I'm going to switch colors here. Let's go with blue. So, so we'll just write down our first one. So 238.92, that's uranium, plus N. N is a neutron, and so that's 1, 0 neutron. And then the comma is our arrow. This is a gamma ray, so we'll do 0, 0, gamma. And then we'll put 239, 92, and that's also uranium. So uranium-238 plus a neutron gives us a gamma ray plus uranium-239. And we'll see that uranium, so 238 plus 1 is 239. That works. 92 plus 0 is 0 plus 92. So that is our correct equation. So that's uranium. And sorry, my uranium kind of looks like a 4. That's a U. All right, so here we've got 14 over 7 nitrogen plus P. P stands for proton, so that's just a hydrogen nucleus. And that gives us an alpha particle, so 4, 2 helium plus 11, 6 carbon. So we'll double check. So 14 plus 1 is 15, and 4 plus 11 is 15. That works. 7 plus 1 is 8, and 2 plus 6 is also 8. So that's our correct equation for that. So now we'll do oxygen. So 18 over 8 oxygen. And then our neutron, that's a neutron. So 1 over 0, neutron. And then B, that's a beta particle, and we're just going to write down an electron. So mass 0, -1, E. And then 19 over 9, and we'll put fluorine. And so 18 plus 1 is 0 plus 19. That works. 8 plus 0 is 8. -1 plus 9 is also 8. So that is our correct equation for that. Okay, so we're now ready to move on to, well, I want to talk a few things about nuclear transmutations. So we're going to go back, and then we're going to do some kinetics. So we do these nuclear transmutations with particle accelerators, and there's a whole wide range of particle accelerators, and I'm just going to show you a couple of important ones. This is a cyclotron, which was at the Lawrence Radiation Laboratory at UC Berkeley in California. And in 1955, I don't know what year this particular photo was. I think it was about 1950 something. But in 1955, one of the reactions, one of the nuclear transmutations they did there is they took Einsteinium-253, they bombarded it with helium nuclei. So with the helium nuclei, they stripped away the electrons, and then they put them into the cyclotron, and they sped them up with these large magnets, and then they bombarded them into the Einsteinium-253, and when they did, they created Mendelevium. Of course, they didn't know the name of Mendelevium at that point, but Mendelevium-256, and then a neutron was given off as well. So that was a early way to make Mendelevium. And then let's see, this is one that's much more recent. There's been a lot of elements. Elements 107 through 112 have been made at the Helmholtz Center for Heavy Ion Research in Germany. And there's a piece of equipment called a Unilac, and this is the Unilac. So that big long purple thing is a linear accelerator. And so it's the Universal Linear Accelerator that's what that's short for. And just to kind of give you an idea, the diameter of this tube on the inside diameter is about 2 meters. There's a great picture on their website of some people inside doing, like, adjusting some things on the inside. And so like a person would fit in there. So it's about 2 meter inside diameter. And that gives you an idea of how long it is. I believe it's like 120 meters, if I recall correctly. But the point is that this is that is a particle accelerator, and they have made a whole bunch of really cool new elements, heavy elements that had never been made before. And it's an international consortium, so people from all over the world come there to work. So one of the equations that they did is they took bismuth 209, hit it with iron 58, and out pops meitnerium 266. Now, when they made it, they didn't know it was meitnerium because it hadn't been named yet, plus a neutron, and that's element 109, and that's just one of several, I think 5 or 6 that they made there at that institute. Pretty cool facility. And that's not all to the facility. If you go beyond, there is, if you go beyond this, there is another section where it goes off into a big circular particle accelerator, and then there's a whole bunch of cool stuff. So this is a whole facility, and they can do all kinds of cool experiments there. So if you want to become a particle physicist, you can maybe someday go there and do some work. Okay, so we're going to look at kinetics now. So we will go through kinetics in this video, and then after we're done with kinetics, we'll stop this particular video. So so for the kinetics here, we're going to find that nuclear decay processes are first order processes. So if I were to say, all right, here is a first order process, the decay of molybdenum, which I love saying the name molybdenum 88. If I were to say, what is the half-life of molybdenum 88? Well, you'd say, okay, well, we started off with 1 gram. Half of that's 5, so we'd go out to 5, and that looks like it's 7 minutes. So it looks like the half-life of molybdenum 88 is 7 minutes. And if we go out another 7 minutes, out to 14 minutes, we should be down to 25% of where we were. Yep, it looks like we're at 0.25 approximately. And if we were to go out to 21 minutes, it would be down to 0.125. And you would find that this would be an asymptote. It would get closer and closer to 0 without ever quite getting to 0. However, if you just wanted to get it down to a low enough concentration you couldn't detect it, at a half-life of 7 minutes, you probably could just, go home for the weekend and come back. It'll be fine. So, so we estimated the half-life there of molybdenum 88. So that is that. All right, and we want to go back for a second because there's a couple of problems we want to do on the in-class assignment. For whatever reason, the little thing didn't pop up, but that's okay. So we're going to go back to the in-class assignment. We're going to do number 33 and 34. All right. So the half-life of tritium is 12.3 years. If 48 milligrams of tritium is released from a nuclear power plant during the course of an accident, what is the mass of this nuclide that will remain after 12.3 years? This is definitely one you don't want to overthink. So 48.0 milligrams, and after 12.3 years, we're going to have half, because that's the half-life. So we would have 24.0 milligrams. All right, that's how hard that one is. All right, after 49.2 years, well, we're going to find if we take 49.2, so I'm going to do clear 49.2 and divide by 12.3, you'll see that comes out to exactly 4 half-lives. So that's easy enough. So we'll do 48.0 milligrams. And after 12.3 years, we'll have 24.0 milligrams. And after another 12.3 years, we would have 12.0 milligrams. And then after another 12.3 years, we would have 6.0 milligrams. Well, that's 3. We need 1 more. And it looks like I didn't leave much room here. 12.3 years. And that's going to give us 3.0 milligrams. And that is how much is left after that. So 3.0 milligrams will be left after 49.2 years. Okay, so let's look at number 34. So we're going to look at number 34 here. And with number 34, we've got It takes 5.2 minutes for a 1.00 gram sample of francium-210 to decay to 0.250 grams. Well, let's just do a little thought experiment here. 1.00 grams. After one half-life, we would have 0.500 grams. And after one more half-life, we would have 0.250 grams. Well, apparently, to get from here to here, it took 5.2 minutes. Well, that's two half-lives, so let's do 5.2 and divide by 2, and that gives us 2.6. So that means our T1 half is equal to 2.6 minutes. 2.6 minutes. Okay, so let's look at the equations for our first order rate law. So you may or may not remember the integrated rate law, and so our first order integrated rate law is this. And it looked a little bit different when we did it back in chapter 14 because these numbers were concentrations, but here they're just amounts. So the amount at time 0, we'll put n sub 0, that's the amount at time 0. N sub t, that's the amount at time t. K is our rate constant, and t is the amount of time. All right, now just like in chapter 14 when we did rate laws, we can also do the half-life. And the half-life is the natural log of 2 over k is equal to T1 half. So that is our formula for the half-life. So T1 half is our half-life. So I want you to be able to solve for any quantity. If you have enough information, you should be able to solve for any of these quantities. So let's look at number 35 on the in-class assignment. Okay, so now we've got how much time is required for a 5.75 milligram sample of chromium-51 to decay to 1.50 milligrams if it has a half-life of 27.8 days. All right, well, let's go ahead and we'll write down our two equations here. And so the natural log of the amount at time t over the amount at time 0 is equal to negative kt. And we have the amount at time t, which is the 1.50. We have the amount at time 0, which is the 5.75. And we're trying to solve for t. We do not have k, but that's okay. We have the half-life. And we know that the natural log of 2 over k is equal to T1 half. So we're going to solve that equation for k. So k is equal to the natural log of 2 over T1 half. And we'll put that into our calculator. And I'm going to raise this up just a smidge here. All right, so natural log of 2 divided by our half-life. So natural log of 2 over 27.8 days. So divided by 27.8, and that gives us 0.02493 days to the minus 1. All right, so now we've got our rate constant k, and we just went to solve for time. So if we solve this equation for time, we'll get the time is equal to the natural log of the amount at time t divided by the amount at time 0 divided by negative k. So the natural log and the amount at time t is 1.50. The amount at time 0 was 5.75. And the negative k is negative 0.02493 days to the minus 1. All right. So we'll just clear all that, and we'll do natural log of 1.5 divided by 5.75, close parentheses, and then we're going to divide that by negative 0.02493, and we're just going to call that 53.9. So T is equal to 53.9 days. Whatever the unit that we have originally, we're going to have the reciprocal unit in our rate constant K, and we'll have that unit again when we do our time. So 53.9 days. We'll put a nice little red square around that. That's our answer. Okay, so we have another thing having to do with half-life, so I'm going to go back over to our presentation. We're going to talk about radiometric dating. So because we have all this math that we can use for first order kinetics and the half-life information, we can date objects using kind of a nuclear clock. So as long as we know how much stuff was in a chemical originally, how much of a particular isotope was in a substance originally, and then being able to measure that radioactive material now, we can get a good estimate of how old something is. For example, we can do carbon dating, and carbon-14 has a half-life of 5,730 years, give or take a few years, and we'll find that if we've got an object that is under 50,000 years old but older than 1,000 years old, we can get a pretty good estimate of how old it is. Now, the further we get away from that 5,700 years, then the more uncertainty we have. But we can get a pretty good estimate, and this is a good way of looking at prehistory things and determining, prehistory things and determining if they match a certain age range. Now, there are other isotopes that can be used, so carbon is not the only one. Uranium-234 has a half-life of, 245,000 years. All right, that shows up in some rocks. Potassium-40, this one has a half-life of over 1 billion years. That can be used in certain applications to get an estimate of the age of certain rocks. We've got uranium-238 with a half-life of about 4.5 billion years. Well, that's pretty cool. And then here, this has a half-life of 48.8 billion years. Well, that's pretty amazing. The estimated age of the universe, what we know as the universe, is only about 13.8 billion years. So this has a half-life greater than the estimated current age of the universe. Oh, but we have another one. This one's 106 billion years. So we've got a wide range of possibilities to look at for radiometric dating. I don't know how much samarium-147 has been used for radiometric dating, but there you go. So let's look at carbon dating. For carbon dating, we're going to be talking about carbon-14. So carbon-14 dating. That's a particular isotope of carbon. So before we talk about how it gets incorporated, let's talk about carbon-14, how it is created. So there's cosmic radiation, which is just high energy protons that are streaming from the sun through space. They hit our Earth's atmosphere and they run into other atoms, and that creates neutrons. Those neutrons in turn, because they can react pretty easily with other elements, and nitrogen makes up about 78% of our Earth's atmosphere, those neutrons tend to run into other nitrogen atoms. They run into nitrogen atoms, and that creates carbon-14 plus a hydrogen nucleus. So that proton is just a hydrogen nucleus. Well, carbon-14, as soon as that's created, the clock starts on it, and it has a half-life of 5,730 years. Well, that carbon eventually gets oxidized and converted into carbon dioxide. And of course, carbon dioxide is slowly absorbed via photosynthesis into plants. And so if you have a plant that died some 5,000 years ago, then you can get an estimate of how long ago that plant died. Of course, animals eat plants, and other animals eat other animals. And since the lifetimes of these plants and animals usually is much smaller than that 5,000 years, then we're, all living organisms are going to have a pretty constant amount of carbon-14 in them. So we'll find that everything that consumes carbon, which is anything that's living, is going to have a small amount of carbon-14 in their bodies. Once they stop consuming carbon, which has to be the worst euphemism for dying ever, but once they stop consuming carbon, that carbon-14 level will start to decrease at a rate of half every 5,700, whatever the number is, 5,000, I forgot the number, 5,730 years. We will find, again, that the useful range for carbon-14 dating is somewhere between 1,000 years up to 50,000 years. If you get less than 1,000 years, the changes are so small as to be unmeaningful. And if you get over 50,000 years, the amount of carbon-14 left is so small as to be irrelevant. So there is an assumption that is made when you're doing carbon-14, and that assumption is that the concentration of carbon-14 in the Earth's atmosphere is constant. And that is somewhat true, but it is not absolutely true. There is a pattern of solar cycles that causes carbon-14 to go up and down. There are human events where we've created more carbon. There's things that happens in the ocean. There's all kinds of interesting things that can happen. We are going to get an estimate by doing this. So we're just getting an estimate. So let's look at number 39 on the in-class assignment. And after number 39, we will stop this video and we'll do the next video here a little later. So number 39, switch over. It's right here. We've got a wooden artifact from archaeological site, has a carbon-14 activity. Activity is supposed to be proportional to the amount. So we'll use that in place of the amount at time t versus the amount at time 0. This one will be the amount at time t. So it has an activity of 13.4 counts per minute as compared with an activity of 32.5 counts per minute for a standard of 0 age. So over here, we'll do blue here. We'll do the amount at time t is equal to 13.4 counts per minute, so CPM. And then the amount at time 0 is 32.5 CPM. And then, let's see, our T1 half is equal to 5730, so 5730 years. So that's our T1 half. And then after that T1 half, we will now do, let's see, determine the age of the artifact. So we will need to calculate K, and our equation for the rate constant K, so K is equal to natural log of 2 over T1 half. So K is equal to the natural log of 2 over T1 half. So the natural log of 2 over 5730 years. So we'll use the same abbreviation they have there. All right, so we'll do natural log of 2 divided by 5730. And that gives us 1.21 times 10 to the negative 4. And that's going to be years to the minus 1. So now we have a value for K. So now we want to determine the age of the artifact. So we'll go back here. We've got natural log of the amount at time t over the amount at time 0 is equal to negative kt. Not T1 half, just t. And we're trying to solve this equation for t. So let's solve that equation for t. So when we solve that equation for t, t is equal to the natural log of the amount at time t over the amount at time 0 divided by negative k. So t is the natural log, and so the amount at time t was 13.4. At time 0, 32.5. And the negative 1.21 times 10 to the negative 4 years to the minus 1. So we'll do natural log of 13.4. Get that onto the screen there. So 13.4 divided by 32.5. And then we'll divide that by, after I close parentheses, negative 1.21 times 10 to the negative 4. And that gives us, let's see, we've got 3 sig figs, so we'll call that 7,320 years. All right. Now, as far as how confident are we with that number? Well, like the 7,000, we're pretty good. The 300, yeah, the 20 is a little bit iffy. You really can't tell the difference between something that is 7,320 years old versus something that is 7,350 years old. That's just, you're not going to get that level of precision. But you definitely can tell the difference between something that is 7,300 years versus something that is maybe 8,000 years. So, all right. Well, we're going to stop this video. This is our second video in the chapter. In our third video, we're going to pick up with section 21.5.